very well in SPVS, and I really wanted to be able to label peaks, which can't do on Sigma Aldrich. So that's why I'm handing out the handout now, because I had to work up the data on the computer this morning rather than for the weekend. So that's the handout of a couple of the spectra that we're going to analyze. And we're going to look specifically at the coupling constants and how to analyze them today. So that's what we'll get into, and that's what's coming around. I do have some other notes that are just going to go on the board first. So we are going to be talking about coupling of systems, and I believe I have one more slide on the last PowerPoint.
That's the 14th day? Mm-hmm. It's running 12th and everything. Oops.
So we've gotten through all the different types of coupling, and we just had one more slide here, which is just a way that we can talk about coupling. And so this is the Popal nomenclature system. And in this, you look at groups of atoms and label them as A, B, C, or M, or X, Y, Z. And the way to determine that is to look at how close together the two peaks will be in the atomography. So if we were looking at this system here, where we had a CH2 group and a CH3 group, we know that those aren't going to show up as the same signal, but we're going to label them as A, on the end of the chain there, and then X for the CH2 group, meaning that the difference between the chemical shifts of those two is going to be pretty large. So we know that the CH3 group should be between 1 and 2, but the one next to a CH2 group next to an oxygen should be between 3 and 5. So that's a pretty large difference. And so we'll label that as AX. And in this case, we're going to have A3X2. So there's 3 hydrogens that are at A and 2 hydrogens that are at X. And when we talk about some spin systems, we're going to talk about A and B's and C's in the systems. The aromatic ring, we have talked about them being symmetrical, so that these 2 hydrogens are going to show up in the same region, and these 2 are going to show up at the same signal. They are symmetrical and equivalent in terms of their chemical shift, so they're chemically equivalent, but they're not magnetically equivalent. And the reason for that is that this proton here, let me draw it in.
Is this for H anymore?
Yes.
Why is it A3?
Because there's 3 of them. CH3,
Oh, okay.
CH2.
And what is the delta V or mu or whatever?
Same delta frequency or chemical shift.
Oh.
You know, they are proportional, or they have a relationship. So these 2, if we call them HA, are going to show up as the same chemical shift. But as we talked about on Friday, we can do long-range coupling, especially when you have alkenes or an aromatic system. And so these are actually not magnetically equivalent because they have a long-range coupling, the J1, 2, 3, 4 between them. And so we're going to label this as HA and HA primes to indicate that they are different protons. So when you have magnetically inequivalent protons, then they get prime numbers.
Can you say that again? They're not equivalent. So they're
When they couple each other,
so not coupling each other exactly the same, right?
well, they couple each other, which means they're not the exact same thing. You can only have them be magnetically equivalent if they're not coupling each other. and they have to couple everything else in the exact same way. So these are considered chemically equivalent, but not magnetically equivalent. We also have hydrogens here and here, and those have a different chemical shift. So we're going to call them HX, and that's going to be, one of them is going to be HX prime, because again, those are magnetically inequivalent. And we'll use a prime next to that to indicate that they are not equivalent. So total of the system, we have an A prime, an X, and an X prime. And we'll be using this kind of nomenclature.
How did you assign them as X instead of just like AA prime, BB prime?
The chemical shift between these two is relatively large because one of them is an NO2 and one of them is a methyl group. So even though they're close to like maybe the 6 to 8 range, they'd be shifted because of that, and that's going to separate them out enough that they're very dissimilar. They'd have to be pretty close together to be the same, and we'll see some examples of that. So we have kind of 4 different protons we're looking at, even though we are going to only see 2 sets of signals, and they'll integrate as 2, but you'll see some extra splitting when they're splitting each other.
So the magnetic equivalence, is that something you see on the MR, or is that something you see on a different scan?
No, we'd see it in the NMR in this case because we'd see that really tiny splitting. So it's a J4 coupling. And if you remember, a J4 coupling is going to be, so it's going to be the A to A prime. And it's going to be probably between 0 and 1 hertz. In order to see that, you'd have to zoom way in on the spectrum to see it.
Why is it, I'm sorry, why is it J4? Why is there a 4 there?
1, 2, 3, 4 bonds.
4 bonds are
Yep, the 4 indicates how many bonds it is between them.
What about the methyl group? Would that just be Z?
Yeah, be some other letter.
Okay.
Let's talk a little bit more about this magnetic equivalence and equivalence. So here's another example we could look at with that as a system. Just do one more labeling. And this one, we probably have to see the actual spectrum in order to determine whether they are A or B or M or X. So in this case, we have a hydrogen here, here, and here. So we're going to talk about this as an A, and then a B, and an X. It could also be a MX for the 3 different hydrogens, depending on how close their chemical shift values are. When you're doing this kind of nomenclature, note that this is for the spin system. So it's the protons that are actually coupling each other, and that goes back to the CH3 group. It's not likely going to couple at all, and so we wouldn't include it in the spin system. So I'll ignore these CH3 groups as well. So not coupling with this. So this could be a BX or a MX, just depending on how close these chemical shifts ended up being. There are going to be some systems like that are magnetically equivalent chemically equivalent, but not magnetically equivalent.
I had a question about the, not the aromatic, the other one. If, say that, that R group is another ether coming off, would then be like A6X4, or would you give them different?
Yeah, if it was symmetrical, we could do, well, do we want to do that? I think we'd just leave it as this, and then you just have 2 of them, because it's not like there's going to be 6 A's coupling to 2
Right.
X's. So you wanna just go within the one system that's coupling, and then your integration is going to be different, but we're just talking about the
Okay.
coupling pattern.
Okay.
So you don't wanna indicate that it's gonna be a set pattern. Yeah. So far we've looked at fairly simple molecules, and we want to look a little bit more at enantiomers or diastereomers, and that's going to throw off the spectra quite a bit. So for group equivalents, we have several different options for geminal groups. Remember, these are CH2 groups where you have two hydrogens attached to the same carbon. For the most part, what we've seen so far is they're homotopic. In a homotopic, they are always equivalent. So let's say we were looking at these two methyl groups. Those two methyl groups are always going to be equivalent. If we were to replace one of them with a CD3 group, the two groups are still going to be in a plane here. We have a plane going down the center here, so they're still the same, which means that, or we don't create a stereocenter when we do that. That means that these two groups are always going to be the same regardless, and they're always going to show up as one signal on the NMR, and they're not going to couple each other.
Wait,
So we do not create a stereocenter when we add the CD3 group. That's going to be kind of our test when we're looking at these. Sammy?
why doesn't it change it because it's different than
Well, we'd see a different signal, or we'd see a different NMR if we actually made this molecule, but
Okay.
we're doing kind of a thought test here. If
Okay.
we replace that CH3 group with a CD3 group, we do not create a stereocenter.
Okay.
The other examples will. So enantiotopic, when you have that same molecule, but instead if we substitute the hydrogens on the CH2 groups here, if we were to substitute one of these with deuteriums, actually I'm just going to change one of them. So we change one of those, we create an enantiomer of the original compound. So our deuterium replacement has created a stereocenter at this position. An enantiotopic group, when you replace one of them, is going to create an enantiomer. However, when we look at the original spectra, they are going to be equivalent in an achiral environment. Normal environment, so if you were to put it in chloroform and run the sample, you're going to see those two H's showing up as the same signal, which is what we've been seeing and expecting. If, however, we were to put this in a non-chiral environment, or in a chiral environment, like in a chiral solvent, all of a sudden those CH2s are going to be inequivalent. Because they're going to interact with the chiral solvent in a different manner. And if you're in biochem, you may also see this in when it's bound to an enzyme. So the two hydrogens of that CH2 group are going to have different, or be different enantiotopically. For the most part, this doesn't affect our spectra at all, because we usually don't use a chiral solvent. It's very expensive to get a chiral solvent, and we're not dealing with stuff with enzymes. So enantiotopic for NMR that we're practical purposes are going to be equivalent. So that means they are going to show up as the same signal, and they are going to couple everything else equivalently. The last category that we have here is going to be the diastereotopic. And if those didn't create anything, that means we're left with something that is going to create something different. So let's say we were given this molecule. This molecule has a stereocenter already. And now if we look at the CH2 group here and here, if we were to exchange one of those for a deuterium, we are going to create a second stereocenter. And if you remember, if we have one, so if we have one stereocenter, you can create an enantiomer of that compound by flipping the chiral center. If we have two, then we have the possibility of creating diastereomers. This deuterium, which is on the same side of as the OH, is different than the hydrogen. And likewise, when we look at these in NMR, this hydrogen that's on the same side as the OH is going to show up differently than the hydrogen that's on the opposite side of the OH. And we see two different signals, and it's going to split, or potentially have different coupling constants with their neighbors. And this is going to create things that do not follow our n+1 rule. That's what we're going to focus on and look at today. So diastereotopic protons. In this case, we're talking about these two, are not equivalent by NMR.
Whereas, like, for the homotopic, they'll always be equivalent.
Mm-hmm.
Even if you change something.
Yeah.
Okay.
Enantiotopic are equivalent in the original sample in an achiral environment. Now, if we actually made the change and created the stereocenter, that changes everything, right? So here we have the two CH2 groups that we were looking at. We also have a CH3 group over here. If we change one of those of the CH3 group to a deuterium, what happens? Do we create a stereocenter or not?
No.
No. Since we don't create a stereocenter if you change one of those hydrogens for a deuterium of the methyl group, then those are not considered diastereotopic. Only if you can change one of the hydrogens and create a stereocenter is it diastereotopic. So methyl groups aren't diastereotopic. It's only CH2 groups we're looking at.
I mean, they're homotopic.
Yes. Since I just handed back that slab, so lots of examples of this spectrum. Citric acid has two hydrogens that are actually not equivalent, and they couple each other, and so we see this kind of weird looking signal, even though you would expect just to see one signal. So those are not equivalent. If we were to change one of these, we would get different relationships between the hydrogen and the oxygen. This one looks a little different because it is symmetrical, but when you the hydrogens here, so if this was here, the two different hydrogens feel a different environment depending on whether they're on the same side or opposite sides of the OH. That would actually be an example of diastereotopic protons in an achiral molecule. The reason why, if we were to draw that out, when I replace one of those deuteriums with a hydrogen, the deuterium, or the carbon with the deuterium on it, is now a stereocenter. And because we've created that perturbation for this center as well, it is also a stereocenter. So we actually create two stereocenters by replacing one group, because this original molecule was meso, funny meso category that was not chiral, even though it potentially could have been.
So it didn't have a stereocenter before.
But when we draw the substitution test, it has two, and now they're diastereotopic, because you can create diastereomers.
Okay.
If you were to replace one and it makes enantiomers, then they're enantiotopic. So if you have a stereocenter, things become much more complicated. So far we've looked at pretty simple splitting patterns, but now we're going to look at less complicated, or more complicated, excuse me, coupling patterns. And from now on, do not assume that a quartet is a quartet. But there's a couple things we need to look at to determine whether it is a real quartet or not. So, if it is a real quartet, so where did I want to start with that? I had 3 points. I read that, so I should probably talk. It's more organized that way. I say that? No. That's okay. Unless I did it. Yes, what's the information? I guess I did override something. So first thing to look for is a standard splitting pattern that has extra peaks. So let's say you have a quartet, but you're seeing like a little peak in between those, and that's a hint that is not a standard quartet. That's kind of the easiest way to identify that it's not quite the standard one. The second thing to look for is that the signals don't follow Pascal's triangle. I've actually introduced this before with our doublets of doublets. If you have 4 peaks and they're all equivalent across the top in intensity, that means that it is not a quartet, because we know that a quartet usually has to have 3 to 1, or 1 to 3 to 3 to 1 in your pattern. So these are not equivalent, and this is not a quartet. The last one is your final, there may be one more point. Last one here that I have on the board is that the J coupling constants are not the same for every peak. So let's say we have a quartet that looks pretty close to it. But we have a peak that looks like this. This is actually kind of similar to what the citric acid looks like, because the distance between these 2 peaks and the distance between these 2 peaks is not the same. So if these 2 signals are not the same, then it is not a standard splitting pattern. So there was one.
So if it's not a quartet, what do we call it?
Well, we'll get into that. This one is a doublet of doublets. This one's actually a doublet of doublets. Oh no, that one might be just a doublet. Isn't it? 2 doublets that are 2 signals that are slanting towards each other. And we'll see examples of that.
How do we know that the one that you said is not a quartet, that it's not 2 doublets or 4 singles?
Like this one?
Yeah.
You would have to tell based on the integration value. So if this integrated to 1 compared to everything else in your spectrum, then you have to group them together and figure out what they are. If they potentially could be different singlets that are just close together, but you just have to use some intuition to decide that.
What kind of a molecule would, or like molecular compound would have 9 plus 1 splitting?
Well, if we have a stereocenter,
Okay.
we're going to have non-n plus 1 splitting. That's the most common one. The alkenes that we talked about tend to have non-n plus 1 splitting because your 2 hydrogens, if you have 2 hydrogens on the alkene, they're not going to be equivalent, and they are probably not going to have the exact same coupling value to everything. And so you see non-n plus 1 coupling. I'm trying to remember what my last point was there, but I thought of it and I forgot. I'll figure it out. So the first spectrum that you have there is of this malic acid. Malic acid, this is in water, so it has, or D2O, it's taken away all the OH and the 2 carboxylic groups. And we don't see those signals, so those have been replaced by deuterium. Now, in order to assign all of these, we need to measure the coupling constants between the peaks on the spectrum. In order to do that, you need one of 2 ways. You need to have the parts per million value of the peak, so the chemical shift of each individual peak within the signal. Or you need to have delta and have the spectrum open in order to measure it. If you have the parts per million value, so I believe this is 4.32, high resolution one, there we go. 4.3258 for our most downfield signal there, and then we have 3208 in the next one over. So you have to subtract those to see the distance between them. Remember that these are in parts per million. And so you get 0.0050 parts per million distance between them. The J values are always reported in hertz, not parts per million. And our chemical shift is equal to the frequency of our signal in hertz divided by the spectrometer frequency. Although now that I think about it, I think this is on a higher resolution one. So we're going to make the math work. So if we want to convert this from parts per million into hertz, we have the delta, we need to multiply. Sorry, this is not hertz, it's megahertz. So we have 0.0050 parts per million times 400 megahertz. What's that? Two? Yeah, I'm pretty sure this was done on a 600 megahertz. I'll show you why in a second. So there, now we got 3. Which is the amount I measure when I look at the spectrum. I got this off the internet, so doesn't crashed. Or didn't crash, it closed on me. So if we open up the spectrum, we actually did this kind of peak picking in the first lab if you select the 2 peaks. Oh wait, that's not what I want to do. I want to do is select multiple peaks. So I'm going to select this one and this one. You can see that they're both yellow down here, meaning they're selected. And then I hit J, and I get 3 hertz for the coupling constant. So the file, the original file that I'm working up right here, knows what the frequency of the NMR was that it was using. So it's going to give me 3 hertz there. And so the coupling constant between those first 2 is 3 hertz, and that's between the 2 signals of the farthest over doublet. Then I'm going to select, I want to know the distance between this peak and the next one in. And so I selected the furthest left peak of this one and then the furthest left peak of this one. That's going to give me the second coupling constant that I need for the value, and they overlap a little bit. Let me zoom in.
Wait, is that 2 doublets?
So it's 2 doublets, but we only have 3 hydrogens on our molecule, right? And so, we've got 3 different signals. Each of them is corresponding to 1 hydrogen. So it's 1 hydrogen that's split twice. We've got a coupling constant of 3 and a coupling constant of 10.5. We're going to draw out a tree diagram of this to show us what it's going to, how we come up with this doublet of doublets. You can each have one. So using the grid paper, we're going to use a coupling constant of 10.25 for one neighbor and 3 for the other neighbor. Here was our original structure. Based on the chemical shift, which of the protons of the molecule am I looking at?
carbon as the OH.
So we're looking at this hydrogen that's next to the OH, because the OH is going to be de-shielding. Both of them happen to be next to carboxylic acid, so that part's equivalent, but the OH there is de-shielding even more and moving it to the 4 region. So we're looking at this proton right here. For HA, we've got what started out as one signal, got split into 2 peaks by one of its neighbors. Let's see. Yeah, that's a constant. Okay, so JAC actually is the 10.25 hertz, which gives us a doublet. So that's now split the peak into 2.
How do you know it's A to C?
I am almost 100% confident. I can't say for sure that this doesn't rotate into another conformation, but I believe this would be the low energy conformation. Have the 2 carboxylic acids opposite each other. When we do that and we draw out the Newman projection, you see that A and C have a 180-degree relationship. So going back to Friday when we talked about the Karplus relationship, 180 being on the high end of the J coupling, and then 60 being on the low end. So the 2 that are right next to each other are on the low end. That's as far as I could find. I didn't find definitive evidence on that, but I'm pretty confident in that. So JAC has split it once by 10.25. JAB then is our, we're going to make that smaller. So if that on your grid was, I would make it maybe 5 squares across on either side. If you did a 3, then we're going to do like 1.5. Make it much smaller.
Wait,
And
so
that's,
it splits first by the 10?
yeah. It's
Okay.
easier to do it with the largest one first, just because it's easiest to draw. They don't overlap or crisscross as much.
Okay, okay.
They may end up crisscrossing eventually, but you can avoid the crisscrossing as much as possible if you start with your largest coupling constants. So then we draw out the second set of peaks from the JAB coupling, which is 3.0 hertz. Now since JAB and JAC are not equivalent, we get 4 peaks that are all equal in value. So if we started here at 100%, this one's now 50% of the original, 50% of the original, 25, 25, 25, and 25. So now we have 4 signals, and we are going to call this a doublet of doublets. So it's a doublet that's been split a second time into another doublet, and we call that a doublet of doublets.
I'm sorry, so the first split, there should be 10 squares, you can't hurt C3.
Yeah, yeah, about. And then your second one would be 3.
So I was under the impression that you only did, for these 3 diagrams, you only used 1 coupling constant.
We did that for the simple system. Now we're going to the more complex systems. So our simple system, we did examples of this, where you had 3 neighbors and they all had the exact same coupling constant. And you got your nice quartet that we are used to seeing, and we saw how they lined up so that you'd get the different ratios of the peaks. Now we're gonna use them to explain our more complex ones, and they're gonna have different coupling constants. This spectrum also has two other signals that are also doublets of doublets. Doublets of doublets are pretty easy to tell that they are doublets of doublets, because you're gonna have 4 lines and they're all going to be equivalent. And we want to look at these and measure their coupling constants. So we've got a 3 hertz there. That's great, because we have to find the coupling constant that matches this one, right? This one. We need something that's going to couple between this signal and the other 2 signals. Here we're going to have another one. So we have 15.5. And then we are going to find 2 more of these. We're a little bit on it. It works better if I go with these ones over here. 10.25 and 15.5. So what this tells me, the 15.5 is the coupling between these 2 signals. So that's the coupling between B and C. So our JBC is going to be 15.5 hertz. Our JAB, we already determined, was 3 hertz. And our JAC is our 10.25 hertz, which then helps us to assign all of the peaks, because the closer coupling here with the 3 then tells us that this is B of our molecule. So if we go back to our PowerPoint slide here. We've got our different hydrogens. So we have HA, HB, and HC. So HA is this one, HB is this one, and HC is this one. When you're measuring coupling constants, you should be able to find 2 different peaks that have that same J value, and that tells you that they are coupling each other. And when you get into some things that have maybe 3 triplets in a quartet, if you measure the J values, you'll be able to assign which ones are coupling each other, and you should be able to put them in order on the molecule button. So the coupling constants can give you a lot of information, even on simpler spectra. This is about as simple as it gets for our more complex coupling. So we're going to do some more examples, Sheldon.
So, would you not find a J value of 15.5 in the H of A at all?
No.
Because there's no coupling between H of A, well, I mean, there's coupling between H of A and B and C, but it's not the 15.5 hertz that's shared.
Right, the HA to HB has a different coupling constant to HA to HC. And so you don't find the 15.5. That's only between the 2 that are right next to each other. Sammy?
I think I missed how to tell which number goes with which hydrogen. I don't think, like, how did you know that 15.5 went with B and C?
15.5 I can tell because they are the ones that are these 2 peaks that are more upfield.
Okay.
And they're less, or more shielded. And just based on the molecule here, I can tell that those are going to be those 2 signals.
Okay, so the chemical shift value.
Chemical shift value can help you discern that. And then for, the AB and the AC I did based on the angle. Again, I may have those backwards, but I'm pretty sure it's this way.
Okay.
What's that extra little guy in H
I'm not sure.
That'd be like
I think it's an impurity or something. This was done in water, and I'm not entirely sure what it is. So if you look at the whole spectrum, it actually has the water with the pre-saturation where it's kind of getting rid of it. And yeah, some type of impurity. I don't think that's one we want to interpret. That's the other thing that can make these things difficult. Lauren?
Is there any way that we could tell a definite difference between like a doublet of doublets and just really, really poor shimming?
I usually look at my solvent peak to see if it has the splitting that it's supposed to have.
Okay.
And so if you look at either your TMS peak, so let's say you have something that looks like this and you're wondering if it's really a doublet of doublets, look at your TMS peak. If it's a nice sharp signal, then it is likely that this is good because the shimming affects all the way across. But if it has that same kind of value, same type of pattern, it's probably just due to bad shimming.
Okay.
That makes your life more difficult. It's possible to interpret. Any other questions? Let's look at another example. No. This is a huge molecule, but I want to focus in on this alkene region and the protons that are on the alkene and then the CH2 group next to it. So we're going to look specifically at these ones. With this alkene, we have with this molecule, we also have a stereocenter, which complicates things a little bit more. So our CH2 group, the two hydrogens are diastereotopic, so they probably are not going to show up in the same area. So we're going to get extra splitting from those.
From which two hydrogens?
The two hydrogens of the CH2 group. If I point to that stage, it doesn't help you much, does it? The CH2 group between the quaternary carbon and the alkene are diastereotopic.
So that creates two stories.
If we were to replace one of them, we would create another stereocenter, because this one is already a stereocenter. And then we have the alkene protons are all going to be different. So we are going to look at these in more depth, but in order to do that, you really got to zoom in on the peaks. I think that was my last point on looking at coupling, is zoom in on your peaks, because when we zoom in on our peaks, we see little tiny couplings that we may not see otherwise. So here's our alkene region. If you go back to this, you see that we have a 1:2 ratio of our two peaks here. And then we have 1, 1, and 2 here. So we have two different, one hydrogen on the alkene and then another one showing up. And I just found this, so we're going to do it together. Draw this coupling. Just trying to decide where to start. Let's start with the hard one. The one hydrogen here is going to be the more complicated one. It looks like this is going to be our CH group that's in the middle. So it's probably going to be that. Let me load up that spectrum.
Wait, so how do you do that one again?
We're going to confirm that once we go through the coupling, but it's one hydrogen and it looks like it has some larger values of coupling.
Give me the spectra, tell me what it looks like. That's what it should
It may
be.
be off on that assignment, so we'll check our coupling and then decide what we want it to be. coupling constant. Okay, so we need to find some J values. In order to do this, I have to have it bind over the piece. Let's see if I can do that. Alright, let's add some piece in. Well, just by zooming in on this, you can tell that it is definitely not a standard splitting pattern because we've got those extra peaks that we're looking at, right? Oh. We have negative values, but that doesn't matter much.
What?
It's just because it's trying to set my reference at 0 way down here. And
Oh.
so it's kind of off, but our J values are not going to change. So we've got 7.06 between the first two peaks here. .02 for the next two peaks. And I'm always starting with the one on the outside and going in to determine my coupling. So you're going to have a smaller coupling and then a slightly larger coupling. You can kind of see that. Remember that these are 3 hertz. So between here and here is going to be 10.25 hertz. And between here and here is going to be 10.25 hertz. Yeah.
So if it, more common than you would expect that second value to be like 14.
So if it were, yeah, if they were overlapping, it would be exactly double. Right? So let's look at what the next one is. And it may be, it's pretty close to double, but it's not quite there. And this one, so this one, what do we have, 17.06. Some of these get rather complicated once you've kind of decided you like some of them, or some of the values you found. You may want to, well, I'd like to check with another peak in the spectrum. Remember that another one within the spectrum is going to have the same coupling constants. So let's look down here. We've got 4 peaks here. 1, 1, 1, and 1. The group we're looking at right now, that CH2 group, should have, if they're diastereotopic, they'll be splitting each other, and they have one more neighbor, right? So we're going to have doublets and doublets for each of those signals. These two are just doublets, so those are not what we're looking for. These two are the ones we're looking for our doublets and doublets for that CH2 group. This group.
Wasn't it doublets? We were looking at that one. Why were the
That's a
balance
little bit
moves
large.
really
We don't
low?
see coupling constants quite that major.
Because she says,
Yep. So if we went from here to here, 143. That would be okay for like a 1-bond coupling. We talked about that, but nothing larger than that. And you don't have HH 1-bond couplings unless you have hydrogen gas. So there's a mention, so that's not a problem. So that would be way too big. So we're looking at these two peaks. Unselect here and here. That's one coupling constant. Wasn't that a number we saw before?
Not quite.
Oh, it's close, but not quite, huh?
Stop at 0.6.
Awesome. Are we looking at the H onto the alkene or the CH2 group?
The CH2 group. So that one's 13.73. That one's also 13.73. This one, this one.
6.
So we've got a 6.86 and a 7.65. Oh, where are all our values here?
switch to the seat.
No, we're not gonna cry, we're gonna finish. Because we are at the end of time here. So we'll go through and assign those